Hello, good morning. So, in this lecture, I'm just going to discuss digital filter structures, which we had already discussed in the class, but I think I should again give a brief review of the same topic. So, dear students, let's start the filter structure. Okay, so the first thing is in this lecture, we'll see the introduction to the filters basically, or digital filters, and there are different structure of the filter like IIR filter, infinite impulse response filter, and so this is your infinite impulse response filter. Then we'll discuss the finite impulse response filter structures. So let's move. Before starting, why we need filters? Okay, there are many application of filter, but some of the applications can be seen as it can be used for separating two mixed signals. If the two different signals have been mixed, we can use it for separation. We can also use it for signal restoration. If the quality of the signal is degraded while acquiring the signal or because of any other reason, we can just restore the signal. So again, the separation of the signal is nothing. We are separating the desired signal from the undesired signal. So undesired signal can be noise or it can be an interference. Signal restoration, basically, in signal restoration, a poor quality signal can be restored to improve its quality. So sometimes you take image and using camera, you capture an image using camera and your hand is shaking. So what you'll see that your image will be a blurred image. So to reduce that blurredness, we can do some filtering process. So in that way, we can enhance the quality of the signal or the image. Okay. So generally, filter is a system that is designed to remove some component or modify some characteristic of the signal. Very basic example, suppose we are taking you have two signals, say of 1 hertz and 2 hertz. You have two signals, two tonal signals, and you have mixed them. Okay, so the combined signal is having a signal of frequency 1 hertz and 2 hertz. Suppose if you pass this signal through a filter having a cutoff frequency, say 1.5 hertz. So what will happen? The output of that filter will contain only one sinusoidal wave, that is of 1 hertz. It will filter out it will filter out 2 hertz sine wave. However, if you are using a high pass filter, say again having a cutoff frequency of 1.5 hertz, in that case the output of the filter will be a 2 hertz signal, and it will filter out the 1 hertz signal. So digital filter, it's again whatever we are discussing, we will just concentrate on the LTI system. We assume that filter is an LTI system, basically linear time invariant system. Okay, so the input to a filter will be again a discrete time signal, or it's a sequence of numbers, and the input is a sequence of numbers and the output is also a sequence. So there are many structures uh, of the way we can realize the different digital filters. We'll see in this lecture. Okay, and these implementation or these structure implementation of the filter, it can be in a software based implementation or it can be hardware based implementation. You can implement it on a hardware. Okay, you can implement it on FPGA basically, or you can implement it using a general purpose computer or any other processor, or it can be hardware software co-design. Some part of the digital system can is implemented in a hardware and some part is implemented in the software. Anyway, it depends on the application and the resources available with us. Okay, so there are two types of digital filters, as we already know, And these digital filters can be implemented in two ways. Basically, these can be implemented in two ways. Okay, number one is, suppose you have an impulse response of a filter and you have input signal. So what will do, the output, you can generate the output by convolving the impulse response with the input signal. Okay, so you have two sequences, one is input sequence, the other one is the sequence of a impulse response. You can just do a convolution operation between the two, and then we can just generate the response of the filter. Okay, so this is also, we can say that each output sample is calculated by weighting the input samples and adding them together. Okay, second method of filtering basically here is based on recursion. Basically, in this case, the each output sample of a filter is depending on the current sample as well as the previously generated output samples. I repeat, the the output sample of a filter is depending on the present input sample as well as the previous output samples. Okay, and mathematically, basically, this is recursive, is it generates a recursive equations basically. Okay, and we call it recursive filter. And if you see, the impulse response of recursive filter are composed of sinusoids that exponentially decay in amplitude. Okay, so anyway, those filters we name it IIR, infinite impulse response filter. Okay, so before starting the structure of the filter, I should introduce the basic elements of the filter structure. Okay, the first one is the adder. So adder has two inputs and one output. It will add the two samples. So the symbol is this. So here you can see this is the input. Okay, second input, and the output is this. Okay, the other one is the multiplier. Multiplier is again where the input is, it's a single input and single output system. So if the signal coming over here is say xt, if the input over here is xt, the output over here will be a into xt or xn. This is a multiplier. Then we can have a delay element. Basically, delay element, it just delays the signal, just like uh, uh, a shift register does basically. So if you are giving consider a D flip flop where you have input and you have output. So the input will go to the output terminal only when clock edge occurs. So in the same way, so the clock edge occurs only after definite time interval. So it depends on the time period of the clock. Okay, so the signal at the output is delayed by how much time? The time which is equal to the time period of the clock. We represent it mathematically something like this: z inverse. If the input over here is xn, so output will be xn minus 1. So if the input over here is say xn, sorry for this, anyway, I could not draw it on this screen because there is no facility for writing on the touch screen. Anyway, so the multiplier can be represented like this. This is the multiplier. Basically, you can represent it like this, and the sorry, the previous one. Sorry, this one is a adder. This one is a multiplier, and this one is a delay element. When we draw the signal flow graph, so we'll be using these symbols for adder. This symbol is for multiplier, and this symbol is for delay element. Okay, so let's start with this. Suppose we have a system where input is xn and the output is yn, and this is a block diagram. Here you can see an adder, you can see delay elements are there, multipliers are there. These are the multipliers multiplied by b naught, multiplied by a1, and multiplied by a2, and these are the adders, and these are the delay elements. Uh, so here the arrow indicates the direction, the signal flow direction basically. We can just draw the signal flow graph from here. So we can just replace this with this representation. So here you can see that dots are nothing, are equivalent to an adder. Basically you can assume that these are the adder. The signal is coming from here, the signal is coming from, signal is coming from here, signal is coming from here, and that has been added up, and this is producing, it is producing the signal in this direction. Okay, so let's write down the difference equation based on this system. And basically difference equation is nothing, here we are finding the relation between the output yn and the input xn. So that's the thing which we will be doing here. Now at this node 1, the input is coming xn and that is multiplied by v naught. So at this node, what should be the output? The output should be b naught xn, and here it will remain same, and which is equivalent to, basically you can say yn. Anyway, let me just write down the equation here. So the w2, the output at this w2 is the output at this node, and which is equivalent to a yn basically. So we can just say y w2 is equal to yn, and this w3 is at this node is nothing, it's a delayed version of the yn. Here you are getting w2 or yn, so here we are getting w2 n minus 1. So you can say that y3 is nothing, it's a delayed version of w2, which is equal to y of n minus 1. Then w4 is again a delayed version of this w3. So the at this node w4 will be equal to w3 minus w3n minus 1, which is equal to yn minus 2, and so on. The same way we can just like write w5 is at this node will be nothing, the signal coming from here and the signal coming from here. The signal coming from here will be a1 multiplied with w3, and the signal coming from here will be basically a2 multiplied with the signal coming over here. So we can just write down the w5, and that we can write in terms of y, and then we can just write the w1, whatever signal is coming at w1, the signal which is coming uh, at this node is nothing, it is equal to b naught multiplied by xn, and the signal which is coming from here, from the signal which is going from here. So we are getting this equation. So ultimately as you know that uh, the output will be equal to this signal addition with this signal. So the yn, the output yn is nothing, it's b naught multiplied with xn addition with the signal coming from here. Okay, the signal coming from here is a1 y of n minus 1 and a2 y of n minus 2. So that's all we are getting at this point. So we are able to generate the recursive equation, and if you know the recursive equation you should be able to draw this structure. Okay, so what are the major factors that influence the choice of a specific structure? That depends on the computational requirement. Computation requirements is the number of multiplications, divisions, additions, and all those things. So accordingly we select the available structure. The other thing is the memory requirement. Basically memory requirement, if you are introducing a delay, basically you are introducing a shift register, and shift register is nothing, it's a memory basically. So introducing more delay element basically means you are introducing, you need more memory. So basically memory requirement refers to the number of memory locations required to store the system parameters, past inputs, past output, and any other intermediate computed value. Okay, the other major factor is the finite word length effect. You are storing uh, uh, parameter in filter parameter in a memory, but your memory is having a finite precision. You can store a number, say a decimal number. You can store it in 8-bit or 16-bit or 32-bit or 64-bit. You cannot have the word length cannot be infinite. Okay, because your memory is limited, your word length it will be limited. It can be a 64-bit. You can store a number in 64-bit or 32-bit. So what happens, just take, let's take an example of a pi 22 by 7. So you know that it's an infinitely long number, decimal number. So if you need to save this number without any quantization error, so you need infinite memory element to store that number. But because of the limitation of the memory, we are just fixing it to some memory. We are just truncating it to some bits, like to a 32-bit. We are storing it in a 32-bit or 64-bit or 16-bit, depending on the availability. So we are truncating it. So basically this truncation, sometimes we use rounding operation also. So basically that refers to the quantization effect that are inherent in any digital implementation of the system, whether you are implementing it in hardware or in software. In all those cases, basically the quantization effect will be there. Okay, come to the characteristics of the IR filter. So IR filter have infinite duration impulse response, and the system functions can have poles within this range, basically. Okay, excluding at origin, they're saying. So an IR filter is a recursive system. So you can see a system, these are hz is equal to the yz and xz, which is written in terms of these coefficients. So yz is a polynomial in z inverse, and xz is also polynomial in z inverse. So here you can see in the numerator the degree is m, in the denominator the degree is n. One more thing is, if there is uh, if all the poles of the system of any system is at origin, in that case and the denominator term will be one only, and the system will become an FIR system. So this system can be written as a difference equation like this. So yn is depending on the previous output. The current output is depending on the previous outputs as well as present previous inputs. This one is important. The IR filter is a recursive system. You can see this is a recursive. This is a recursive equation. This whole equation is a recursive equation, and here the output is depending on the previous outputs as well as present and previous output. You can see that index k is from 0 to m. So k is equal to 0 indicates the present input, and k is equal to 1, 2 and 3 till m indicates the previous inputs. So these are the characteristics of a recursive system or IR filter. Okay, and the order of this filter, IR filter, is equal to n if an is not equal to 0. Is equal to n. Basically, it's nothing. It's a degree of the denominator polynomial over here. Okay, or you can say in that you just look at this term. Let me just use a highlighter. So just use this term. Here the k is varying from 0, so 1 to n. So basically it's depending, the output is depending on yn minus 1, yn minus 2, yn minus 3, y of n minus capital N. So the it's depending on the previous n number of outputs. So the degree of this, or you can say the order of this filter, this whole filter, is capital N. Okay, so in the filter structure we have a direct form implementation. So in this form, basically the difference equation is implemented as it is. Okay, so there are two parts of this we'll be using two parts of the filter while implementing it in a direct form. Okay, the first part is the numerator polynomial, which gives the moving average filter basically, and the second part is a recursive part. Okay, or a recursive part which is indicating a denominator part. So you can see in the previous slide, this one this one corresponding to the uh, forward path basically, okay, or moving average, and the denominator polynomial corresponding to recursive part. If you talk about in terms of difference equation, in a difference equation basically, this one corresponding to moving average part and this one corresponding to the recursive part. Okay, so it's having two part, moving average part and the recursive part. So it leads, therefore this implementation leads to different versions of implementation. One is called direct form 1 and the other one is called direct form 2 structures. Okay, so that's a difference equation which we are going to implement, and in terms of transfer function or system function, we are just writing the same difference equation is written like this. Okay, come to the direct form 1. Let's see, this is the diff, uh, this is the difference equation which we need to implement. So let's first talk about the feed forward network, or you can say moving average part. So basically moving average part is this only. We are just talking about this part, moving average part. Okay, so this part is implemented over here. So this part is implemented over here. Let's change the, we can sorry, one correction. This part is implemented first. Basically, this one is the moving average one, and this one is the basically recursive part. So first, here they have implemented the moving average one, and this then we have implemented this recursive part, basically where you can see the feedback is there. You can see here, you can see these are the arrows indicating the feedback. So this is a recursive system. Whenever there is a feedback, you can say there is a, that's a recursive system basically, or we are representing it using a recursive equation. Anyway, so let's first concentrate mm, uh, on this part, moving average part. Here the first term will be yn is equal to b naught into xn plus b1 into x of n minus 1 into b2 into x of n minus 2 addition with b3 into x of n minus 3 and so on. So you will see that all these terms have been implemented. Here you are getting first term b naught, in here you are getting xn into b naught, you will be getting v naught into xn. Then at this node, because of this delay element, you will be getting x of n minus 1, x of n minus 2, and so on. So after that, after multiplication of all these individual terms, you are getting here y1n, which is equivalent to this part. Similarly, the recursive part is implemented. You can see a feedback part over here. So it's depending on the yn minus 1, yn minus 2, yn minus 1, yn minus 2 till y of n minus capital N. So all these elements have been generated. Accordingly, they are multiplied with the coefficients a naught, a1, a2, a n minus 1 till a of n. Then all of have been added over here, and you are getting finally yn. So in this way, you are able to implement the two different parts. First part is this. First part of the equation is this, and the second part of the equation is this. So if you combine them, I think I should first clear all those. Okay, now it will be more clear. So we have implemented. This one is your first part. This one is your first part. Or you can say this one is your moving average part, and this one is your recursive part. So if we just bring them together, so this is called DAG form one structure of the FIR filter described using this difference equation. Okay, so come to the DAG form 2. So we know that for an LTI system, you can assume this is the first part of the system, this which is cascaded to the second part of the system. So this you can assume this whole system as a cascade of the two networks. First network is this, and the second network is this. So we can, since the system is an LDI system, we can interchange the order of this system with this system. So let me just first erase all. So if we interchange the order, you'll see, so it will become something like this. Okay. So here you can see first we have drawn the recursive part, then we have drawn moving average filter part. The other thing which you will observe from here is, if you can see here you have Z inverse, then Z inverse, and so on. Here also there is a wall of Z inverse, Z inverse, Z inverse. Now we can see this redundancy of the use of Z inverse. This Z inverse can be mixed with this basically. These two can be combined together. This Z inverse can be combined with this Z inverse, and so on. So if we do that, it's something like this. So in this way, now in this structure, you'll find that you have reduced the number of memory element, which is the delay element basically. So this structure, this overall structure now is called direct form 2. Direct form 2. Okay, so basically the advantage of the direct form 2 is the reduction in the number of memory elements or the delay elements. Okay, come to now, till now we have discussed the filter structure for IR filter. Now let's come to the FIR filter structure, and in this we'll just discuss the direct form realization. First thing is, FIR filter has finite duration, or you can say finite impulse response. Okay, and the system function has the ROC for this mod of Z is greater than equal to 0. Okay, and the other thing, there is no feedback in the FIR system, or you can say it's not depending on the previous outputs. The FIR system is depending on the present input and previous inputs. It's not depending on previous output. So this system is a non-recursive system or non-recursive filter. Okay, and so the other thing is, it's having a finite number of samples in its impulse response, so that's why we call it finite impulse response, and there's no feedback, and so that's why we call it non-recursive system basically. And I had I think I may discuss in future what's the significance of the linear phase system. However, here you can assume that the FIR system can be easily designed to have a linear phase response. Okay, so this is the difference, or you can say system transfer function for FIR filter, and here you can see uh, if you just take this equation and you just calculate the number of poles, so there will be n minus 1 number of poles will be there at origin. Okay, so that's one thing, and the order of this filter will be n minus 1. Okay, okay, now come to the direct form filter realization of filter structure. So here again we are going to implement this equation basically. which is nothing, which you can see it's a convolution between the two signals hn and xn, and the response is yn. So you can see from here that first the xn is there. Here you are getting xn. After delay element, after this delay element, the output at this node will be x of n minus 1. Then again one more delay element, output over here will be x of n minus 2, and so on. At the end you will be getting x at this point basically, because of all delay elements along this line, you will be getting here at this node the signal will be x of small n minus capital N plus 1. Anyway, so all these signals, now you can see at this equation, all these signals are multiplied with different values of h0, h1, h2. So that's why we are multiplying it, h0, h1, h2, h of n minus 2, h of n minus 1. Then we are just adding all those resultant things. Here you can see a summation which is adding all those terms, and that's your output. Okay, so that's a direct form realization, and you can just looking at this convolution formula, you can easily implement this structure. Okay, so one important thing you can see here, it requires capital N number of multiplications. You can see first multiplication over here, second over here, the last one is over here, and in total there are capital N number of multiplications. So there is a linear phase filter, and I think in some other lecture I will discuss that, the importance of the linear phase filter. However, let me just tell you the filter structure for those kind of for FIR linear phase filter. Okay, so the condition for the linear phase is this: the impulse response should satisfy either this condition or this condition. If the system, if the impulse response is symmetric, so it should satisfy the first condition. If the impulse response is anti-symmetric impulse response, it should satisfy the second equation. So these are the properties, and let me just show you some example for the same. Assume that the total number of samples are 11. So the impulse response is starting from 0 and going till 10, and these are the samples. You can see this is a symmetric response with respect to this axis, axis over here, axis over here. So this and it satisfies this above equation. Okay, so that's the case when capital N is odd, or capital N odd means it contains basically odd number of samples. if if the sequence is an antisymmetric, so it is something like this. Basically you can see this sample is equal to negative of this sample. Okay, and this sample is equal to the negative of this sample, and so on. Here also you can see here this sample is, the first sample is equal to the last sample value. The second sample you can see is equal to the second last sample, and so on. However, in this case it's a negative sign is there, so thereby you can say it's antisymmetric. And for antisymmetric, if the number of samples, the total number of samples in the impulse response is in odd, so the middle sample will always be 0 basically. Now this shows the again a symmetric case. However, the number of samples are even, so here the shape is will be something like this. For the case when it's antisymmetric and the total number of samples are even, in that case there's no region existing, there's no zero sample will exist, or in this case. Anyway, so all these are the examples of a linear phase system. So it satisfies these two equations, this equation and this equation. So if it's satisfying, if your impulse response is satisfying any of these two equations, so your impulse response is said to have a linear phase. Okay, so basically here I can just add an statement. Basically, linear phase means the phase response, basically the phase of the system is changing linearly with the frequency. Okay, or the phase is proportional to the omega. It's not proportional to omega square. Okay, it's a linear function. The phase is linearly dependent on the frequency. Okay, and there are some advantages of this. We'll discuss sometime, some of the lecture. Anyway, so come to this case when n is odd. When n is odd, this is the system equation, basically system function. You can just break it into different summation. You can first go till n, summation of 0 to n minus 2 by 2 minus 1. Then the other term will be n minus 2 by 2. The next one will be n minus 2, n minus 1 by 2 addition with 1 till the last term. And if uh, you can just replace this n minus 1 by 2 plus 1 with m, this term with m, and you can just restructure this equation. You will be getting this equation, basically. Okay. And this is the basically this equation. Then further, this is equivalent to, you can say, uh, this can be written, this is equivalent to hn or minus hn or positive hn, depending on the linear phase. Or so this is equivalent to this, basically. So after adding all these terms, you will be getting this equation, which is a linear phase equation. And we are getting this equation after adding all these terms. Anyway, so here the important thing I just want to tell you here is you're getting this equation, and if you're implementing this structure, you can see that you are multiplying hn with two different delay elements, basically. So it means basically if the system is a linear phase, we can reduce the number of multipliers required. So this is the implementation. Here you're getting here xn. Okay, here you're getting xn. Here you'll be getting x of n minus 1. At this node you will be getting x of n minus 2, and till this node you will be getting x of n minus 1, n minus 1 by 2. So basically you can see the chain, the delay element change, something like this. Okay, let's look at this. Here this, whatever you're getting at this node and you're getting at this node, they are multiplied. All of them are added first, then multiplied with this coefficient. Okay, so one way is you can just multiply this term before adding. You can multiply it over here and multiply it over here, then you can add them. So in that case you need more number of multiplications, double of this. So linear phase system basically reduces if we implement the drag form realization of a linear phase system. So it reduces the number of multiplications required while implementing. Same is true for this case. You can say when n is even. So in this case also you can say the multiplication is after addition. Here also you can see the multiplication is after addition, multiplication is after addition. Here multiplication is after addition, and multiplication is after addition, and you're adding them. You can see even from this equation you can see first we are first we are adding them, then we are multiplying with hn. Okay, so that's all for today, and in the next lecture we'll just go into the detail of the linear phase system and their importance. Thank you very much. Thank you for your patience.